Are you seeing the slides?
Yes.
Okay, you can start.
Okay, so welcome to the QuantHub seminar. This is the last QuantHub seminar this season. We will restart in fall. And I would like to add that in fall, we will also have the QuantHub conference, Quantum Technologies and Computation for High Energy Physics, taking place in Bari, Italy from September 25 to 27. Here is the scientific committee and the organizing committee, and the speakers will be announced soon. So stay tuned and mark these dates. And due to the conference, there will not be QuantHub seminar in September, so the fall season of the seminar starts with October. And now I would like to introduce our today's speaker.
Should I share my slides in the meantime?
So today's speaker is Alessandro Roggero, and he will talk about quantum simulation of collective neutrino oscillations.
Wonderful. Thanks, Andres, for the introduction, and also thank the organizers for the invitation to speak here today, and all of you for connecting to it. So in my talk, I want to tell you about the effort we've been doing to try to do quantum simulations of collective neutrino oscillations. So this is a phenomenon that is expected to occur in astrophysical settings like collapse supernova, where the local conditions are extreme, like we have very high neutrino densities. And it's essentially, it's a flavor oscillation phenomenon where flavor oscillations are strongly affected by neutrino-neutrino scattering. And as we are going to see during this talk, simple models to describe this phenomenon will lead us to solve the time evolution for strongly correlated many-body systems, which are very difficult to perform classically, but are actually very well suited to be simulated on quantum devices. So what I'm going to try to show you in this talk are some of the first results we've been obtaining using current day technologies. So to start with, let me just briefly remind you why neutrinos are important in collapse supernova. So neutrinos play a fundamental role in different stages of the collapse supernova. In the first place, at the beginning, when the shock is propagating outwards from the central collision object, neutrinos are the main vehicle to extract energy from the shock wave. And they are so efficient that effectively they are removing enough energy that the shock wave at some point stalls a few hundred kilometers outside of the center of the explosion. Neutrinos are also produced in the cooling of the central object, the proton-neutron star. And these neutrinos can actually re-energize the shock front by depositing energy behind it and eventually lead into a successful explosion. Okay. Later on, after the shock front has been expelled, in outer space, neutrinos are also responsible for pushing material outwards, and in what is called a neutrino-driven wind. And this is the setting where our process nucleosynthesis is thought to happen in the material ejected from the supernova. And neutrinos are actually effectively processing the material that is being ejected. And in particular, they are affecting the proton fraction that is present locally there. So they're affecting also the nucleosynthesis yields. Okay. So all of this happens in just a matter of a few seconds, about 10 seconds. And the system loses about 99% of the gravitational binding energy of the progenitor star. Which translated in neutrinos, it's something like 10 to the 58 neutrinos emitting in just a few seconds. So you can imagine that like the luminosities are very high and the local neutrino density is also very high in these situations. So the only experimental evidence of this sort of standard neutrino-driven mechanism for collapse supernova has been verified 36 years ago in 1987. There was a close enough supernova to us that we were able to actually measure neutrinos produced from it. And they sort of follow exactly the pattern we would expect. Okay, so neutrinos that are of the order of tens of MeVs, which is the usual temperature in these objects, and lasting for about 10 seconds. Okay, so unfortunately, these were sort of older devices that were able to, older measurements. So we only have real information about neutrino energy, okay, instead of like flavor dependence. So with newer detectors that are online at the moment, if we have a similar event, we will be able to collect one, way more statistics, and two, also information about the flavor. Okay, and that's very important because, like, especially in these two processes, okay, charge current reactions are one of the dominant reaction processes that are happening, and these are flavor dependent. Okay, so knowing exactly the spectra, the flavor dependent spectra of these neutrinos is important to understand the dynamics, the dynamical evolution of these objects. Okay, so we know that like flavor changes as neutrino propagate, at least in vacuum, right? And we also know that neutrinos, flavor oscillations are affected by the scattering between neutrinos and electrons, for instance. That's what gives rise to the MSW effect, which is also very important in neutrinos produced in the sun. Something that is very different, however, from the sun in these objects is the fact that like the neutrino density is very high, as I was saying. And in these situations, neutrino-neutrino scattering becomes actually very important. Okay, so if we stick to just forward scattering, so like processes where there is no momentum exchange between the neutrinos, there are two main diagrams that are important in these events. So these are like mediated by Z bosons, and for the energies that play here, they essentially act as contact interactions. So there are two main contributions. The left one is the diagonal. Okay, so essentially it doesn't contribute anything to flavor mixing. So the second one, however, it's off the diagonal and it's equivalent. So we have two neutrinos, one with flavor nu-E and momentum k, and one with flavor nu and momentum q. In the second diagram, they can exchange flavor within themselves. Okay, so the total flavor in the process is conserved as it's the momentum. Okay, but still, this can lead to important effects in the flavor evolution if the distribution of flavor for different energies is very different. Okay, and this is something that we actually expect in these core-collapse supernova scenarios. Okay, so what I'm showing you on the right, it's a cartoon of the fluxes, distribution functions as a function of energy for neutrinos produced in a supernova. The blue one is for the electron flavored neutrino, and the orange one is for new flavored neutrino. Okay. They are very different because the emission surface is very different for them. The electron neutrinos are more strongly coupled, so they get emitted farther away. So there is a strong flavor dependence in energy distribution of these neutrinos. Now, if we let flavor evolution occur with this initial condition, and we also include the effect coming from forward scattering between neutrinos, what can happen? It's something that is called a spectral split, where at a given energy in this particular simulation, it was around 10 MeVs. You can see that like for low energies, the neutrino distributions are exactly the same. So the dashed blue line, it's a final distribution for electron flavor neutrino, and the red one is for the heavy flavor one. Below the split, the distribution is exactly the same. After the split, they interchange. Okay, and this is caused by forward scattering between neutrinos. Okay, and the interplay between that and the vacuum oscillations. So the net effect of this is, as you can see, for instance, we don't expect to see without oscillations to have high energy electron flavor neutrinos. Okay, if we didn't have oscillations. With oscillations, since we are swapping between muon and electron, we are actually producing a higher energy tail for electron neutrino and suppressing the energy for the heavy flavor neutrino. And this can have important effects in both the nucleosynthesis processes and the reignition of the shock wave. Okay, so this is the type of phenomena that can occur when we include this type of process. Now, if we want to try to describe the dynamic evolution of flavor, the simple thing that we can do is to just assume that we just track two active flavors, so the electron flavor and an heavy flavor, which you can think of like as a mixture between a muon and a tiny neutrino. So this can be justified because the other mixing angles that are coupling to the third species are much smaller. Okay, but everything I'm going to show you today is going to be just a two flavor approximation. Generalizations can be done, and we can discuss about them at the end of the talk. But the idea is that when we just look at two active flavors, we can represent the flavor amplitude of a given neutrino with some momentum pi, okay, as an ST2 isospin. Okay, so for instance, we can identify that the spin up state with electron flavored neutrino and the spin down state as a heavy flavored neutrino. Okay, so using this basis to represent flavors for individual neutrinos, we can write down an Hamiltonian that describes to leading order the evolution of these neutrinos. It's divided in three main pieces. The first one here, it's a one-body term, okay? And this essentially represents the vacuum oscillations. So the frequency component here, it's essentially the frequency that you will have in vacuum, which is inversely proportional to the neutrino energy. And B, it's a vector with just points in the direction of the mass basis, okay? So it depends on the mixing angle. The second term, this comes from the interaction between neutrinos and the surrounding leptons, for instance, electrons, okay? The coupling constant here depends on the local electron density, okay? And it's diagonal in flavor space, okay? Because essentially this just gives a difference in energy between electron and muons. So this is all pretty standard. That's the Hamiltonian that describes neutrinos in the sun, for instance. The difference in the Korkov supernova is that we have an additional piece, which comes from this neutrino-neutrino scattering interactions. And you can see that it has a structure of an Heisenberg Hamiltonian. Okay, so it's an all-to-all Heisenberg Hamiltonian, okay, with an overall coupling constant mu, which depends on the local neutrino density, and that's the reason why this only matters when the neutrino density is large enough. And it also contains a dependence from the direction of momenta. So this cosine of theta ij, that's just essentially the scalar product between the momentum of neutrino I and j, okay, and this factor here essentially just encodes the information about the geometry of the explosion. So for instance, this makes sure that like two neutrinos which are propagating parallel to each other, they don't interact, anti-parallel with each other interact maximally, okay? So ideally, we would like to solve for the time evolution under this Hamiltonian of some initial neutrino configuration and study how flavor evolves at long times, okay? Due to the presence of this two-body interaction, however, the exact solution for this time evolution, it's exponentially challenging classically. So the cost explodes as 2 to the n, where n is the number of neutrinos involved, okay? And that's one of the reasons why we were thinking about starting to try and use quantum simulations, okay? So but before going there, let me first tell you about how this problem is tackled classically, okay, in the vast majority of the literature at the moment. And to understand it, so what is usually done is what is called a mean field approximation. Let me try to explain to you what this is in this context a bit quickly, okay? So the main observable we are after here is the expectation value of these Pauli operators for every neutrino, okay? Because they contain the information about flavor for all the neutrinos. And if we look at like the time-dependent the evolution equation for these expectation values, okay, we end up with an evolution equation like this, okay, where pi, it's usually called the polarization vector, it's just expectation value of the polymetric on a given neutrino. And the first part here is just coming from the one-body terms, both the vacuum term and the coupling to electron. And in addition, we have this two-body contribution, okay? So what you see here is that the evolution equation for the expectation values of one-body operators depend on the two-body operators, okay? Which in turn will depend on expectation, whose time evolution will also depend on the expectation value of three-body operators, okay? So this is called the BGGKY hierarchy, okay? And in general, it doesn't allow you to solve this at any given level, okay? So what one can do, which is called the mean field approximation, is to approximate the expectation value of products of Pauli matrices, okay, as the product of expectation values, okay, essentially just neglecting correlation between different particles. If one does that, then it's easy to see that one can re-express this two-body part in terms of polarization vectors, okay? So we end up with an evolution equation, okay, which is a closed system of 3n coupled differential equations, which we can solve, okay? And this can be done very efficiently. For instance, the simulations I was showing you here were done using this procedure, and simulating systems with like 10 to the 4 or 10 to the 5 neutrinos. And here you have two main degrees of freedom. You have energies and angles, okay? So you can do routinely simulations nowadays with say 100-ish energies and 100-ish angles, okay? Which is way beyond what you could do simulating directly the Hamiltonian, okay? So something that is important to try to to understand is whether or not we are missing some physics by doing this, okay? And that motivates try to solve the original many-body Hamiltonian, to try to see if there are differences in the mean field, okay? So I want just to show you a couple of examples of what possible differences between the mean field and many-body simulations can happen. The first one is reasonably simple. So in this simulation here, we took two beams of neutrinos, one starting as electron-flavored neutrino, the other one as heavy-flavored neutrino, and these are counter-propagating. Okay, so they are anti-parallel with each other. Okay, and what we looked at the evolution of the flavor of the excitation value of the Pauli operators on one neutrino. Okay, which one doesn't matter because of symmetry, as a function of time. Okay. What you're seeing here is the expression value of x and y components of the neutrino population vector and the z component. The z component is the one that directly tells you about the flavor. The other two tell you about coherence between flavors. Okay, and the curves you see here, the orange one is the mean field prediction for this setup. The black one, it's a simulation where for each beam we use 64 neutrinos, and the turquoise one is when we use 1024 neutrinos per beam. Okay, the reason why we can go to such large numbers is because of the high symmetry of the model, which we exploit to do the simulation. Okay, so what you see here is that as we increase the number of neutrinos, okay, the results tend to converge slowly towards the mean field values. Okay, especially for the z excitation values. Okay, but there are still significant discrepancies. Okay, which are in general independent. Okay. The reason why we have these oscillations at earlier times than what you have in the mean field, it's essentially caused by entanglement. So one way of looking at it is what I'm showing you here is the neutrino purity for the neutrino we are exploring, what we are looking at here. The purity, you can think of it, it's just a measure of how mixed a neutrino state is. Purity of 1 means we have a pure state of a single neutrino, which means there is no entanglement with the rest. Purity of 0 means the neutrino is completely depolarized, and the entanglement with the rest was maximum. Okay, if you look at the deep, so in these simulations, the neutrino purity goes to 0, and it goes to 0 exactly at the times where the flavor oscillation has the maximum amplitude. Okay, this is a drifter that you can show just grows logarithmically in the size of the system. Okay. But in general, you can see that like entanglement, it's strongly connected to flavor evolution in these systems, and there is possibly strong dependency, so strong differences with the mean field. Okay. In general, for this very asymmetric model, one can show that in the n to infinity limit, that all curves will go to the mean field prediction, but the number that you will need that might be too large. Okay, even too large for 10 to the 58 we saw before. The second example I want to give, and then I'm going to start to show you a few things about quantum simulations. It's a bit less easy. So in this case here, what we're doing, we are looking at the flavor evolution of neutrinos as they leave the supernova. And if you see here, the coupling constant in front of the two-body part depends on the local neutrino density. So as a neutrino flies off from a supernova at the speed of light, it experiences a different local neutrino density. So the coupling constant of the two-body part goes down. Okay, what we're doing here, we are essentially preparing an initial set of initial flavor configuration of neutrinos and looking at the steady state flavor configuration. We are very far away from the supernova. We're just a one body part dominance. The neutrinos we have, so this is a simulation with 16 neutrinos, and we use different energies for the different neutrinos. The black points you have here represent the initial configuration. So on the y-axis here, you see the probability of measuring each one of these neutrinos in the first mass eigenstates, no1. Okay, so these are starting as the first 11 neutrinos are starting as electron flavor, and the other ones are X flavor. Okay, so they both have components in the 1 and 2. And the other curves you see are the steady state solution after we evolved for a long time. Okay. The blue dots are the results of the many-body calculation. The red ones are the results that you obtain using the mean field simulation. Okay, and you see that like more or less the trend is similar, but there are very strong deviations. And interestingly, what we're showing you here also is the green curve. This green curve is obtained by assuming that neutrinos thermalize to thermal density matrix at the very end. Okay, and as you can see, thermal thermalization explains well the results we have in the many-body. Okay, so something interesting that can happen in a many-body simulation of neutrinos is that interacting neutrinos can actually thermalize, which is something that in a mean field calculation you can't achieve. Okay, because for this to happen, you need to have the coherence. Okay, so that's another possible strong difference between the many-body and the mean field. Okay, now before continuing. For full disclosure, I need to tell you one thing. So the Hamiltonian we've been using here and in the previous calculation, also in the rest of the paper, in the rest of the talk, which is this all-to-all Heisenberg Hamiltonian. There is currently a debate in the community, in the collecting neutrino oscillation community, whether or not that Hamiltonian is the right one to describe realistic neutrinos in a supernova. Okay. So I'm not really going to enter into this. If people are interested, I'm happy to talk about it at the end. Okay. So for the time being, let's assume that like we will use this Hamiltonian here as a model which is inspired by neutrino oscillations in supernova, which contains interesting physics, and we want to try to understand. Okay. Whether that gives prediction for supernova, we can talk about it at the end. Okay. Now, as I was saying, it's difficult to calculate, to simulate in general this type of systems for large number of particles. What you're seeing here is a simulation with 16 particles. You need some effort to do. Okay, so something that one can try to do is to instead resort to quantum simulations. Okay, now with this audience, I don't have to spend that much time telling you about quantum computing and simulations. So the basic idea, which was originally proposed by Feynman, is to try and leverage our access to some quantum many-body system that we have full control over. Okay, like for instance, ions trapped in an external laser light. Okay, and what we can do with this, imagine that we want to simulate a separate physical system. Okay, say a system containing a nucleus and a nucleon. Okay, or neutrinos in our case here. Okay, so what one can do, one can map once we discretize the system we want to simulate, we can map one-to-one state of the system we want to simulate to states of the device we have at our disposal. And at the same way, we can map operators acting in this space here with operations acting on the actual device. Okay. Once we perform this mapping, then we can simulate something like a nucleus collision. Okay, as equivalent set of laser pulses acting on the trapped ions on the other side. Okay, this mapping can be done one-to-one. The difficulty of doing this mapping depends on the details of the system we want to simulate and the device we have at our disposal. Okay, but in general, you can think of like we can try to do something like this. Okay, and the advantage is if the mapping is efficient, meaning that like the number of pulses we need to send to this device doesn't grow too strongly with the size of the system, then we can start to simulate very efficiently dynamical processes like say nuclear fusion or neutrino-neutrino oscillations. Okay. So for the purpose of most of the rest of my talk, I'm actually going to abstract the description of this quantum many-body system we have control over as a sort of quantum black box. Okay, that comes to us with buttons that are preparing a fiducial initial system, measuring in a given basis. Okay, and they have a set of possible buttons that are enacting operations, local operations in general on this system. Okay, so this is a sort of digital version of the quantum simulator that I showed before. And it's very useful in general to try to design algorithms to study generic systems. Okay? As we're going to see very quickly, this abstraction might not be necessarily very good when one actually tries to use these quantum black boxes, but we're going to get there in a second. Okay? So this is an interesting idea, and it might be one way of simulating large neutrino large systems of neutrinos. Luckily, in the past few years, there's been an explosion in especially experimental activity in designing and producing these quantum black boxes. Okay, in a variety of different architectures, from the trapped ions I showed you before, to Rydberg atoms, to superconducting circuits, a lot of them. Okay, so with this explosion in the experimental activity, it also came the possibility of access, like for theorists to access these devices and try to use them to do simulations. Okay, so that's sort of like what we try to do. We took our neutrino-neutrino collective flavor oscillation Hamiltonian. Okay, what you see here is that we neglected one of the two one-body pieces, the coupling to matter. Okay, and that's because one can, in first order approximation at least, subsume that one in change in mixing angle. Okay, so essentially we just neglected it in this case. Okay, so we want to assume this Hamiltonian, which contains a one-body part and a two-body sort of all-to-wall Heisenberg interaction. Okay, and the structure of this Hamiltonian is actually very nice. The first thing is that when we use only two flavors, we can fully describe the operators acting on individual neutrinos as just Pauli matrices. Okay, so our degrees of freedom are really just spin 1/2 degrees of freedom, which map very well directly into qubits. Okay, so there is no overriding representing them. The Hamiltonian is also very nice in the sense that like we only have two local interactions, meaning like only two Pauli operators are appearing in every given term in here. Okay, and which means we only have essentially n squared terms, which are also very local. Okay, in Pauli weight. Okay, so this is much nicer than not if we try to do say quantum chemistry, where we have two-body interaction, you will have n to the 4th terms. Okay, so that's also something very nice. Something which is not so nice in general is that these interactions are all-to-all. Okay, and it might be difficult to implement them directly when the device has a limited connectivity. So, for instance, what I'm showing you here on the right, on the top right, it's a diagram that shows you 5 qubits. That's a diagram that represents the quantum device we used for the first set of calculation I'm going to show you. It contains 5 qubits, and the black lines you see here are the connections that are available to perform 2 qubit operations between them. Okay, so you see, for instance, like the term there's going to be a term in the Hamiltonian that couples qubit 2 and qubit 4. Okay, we don't have a direct connection between those, and we need to find a way to make them interact essentially. Okay, so that's a problem for every device with limited connectivity, especially those that are using the superconducting qubits, okay, because of like technological difficulties. So something that we realized when we were trying to do this is that you can actually simulate the full Hamiltonian, okay, without any overhead in number of 2 qubit gates, okay, exploiting the fact that we are doing all the possible pair interactions in here, okay. And the idea, which essentially we borrowed from a construction design to simulate fermions in this paper here, is to use a swap network. So the idea is that imagine we have 4 neutrinos at the beginning, okay, and we want to make all of the pairs interact. Okay, so we need all the pairs to be next to each other at least once in a given sequence. Okay, what we can do, we can swap the location of neutrinos. Every time we apply an interaction, we also swap the location. So for instance, in the first layer, we make interact 1 and 2 and also exchange their position. Same thing for 3 and 4. In the next step, we now have the possibility of making interact 1 and 4. We do that, exchange their location, and we keep going. Okay, that's also called the swap network. Okay, and one can show that like if you have n qubits or n neutrinos with n layers of nearest neighbor to qubit interactions, you can make every pair interact with each other. Okay, the only price you pay is that at the end of the whole sequence, the ordering of the qubits is reversed. Okay, but that's something you can keep track classically very easy. Okay, so in general, if you want to implement this sort of evolution using say a Trotter decomposition where every single piece needs to be implemented, the number of terms you have is n choose 2. Okay, you can use exactly n choose 2 to qubit gates, even if the connectivity of your device is just linear. Okay, because you can coalesce together the swap and the time evolution operator. So that just still takes you 3 entangling to qubit gates. Okay, the price you pay, it's mostly that when you do this, you have an additional overhead coming from like one-body rotations. But apart from that, the number of 2 qubit gates is the same, which is good. Okay, especially because in most devices we always can connect all of them in a linear chain. Okay, good. So now that we found a way of like mapping our Hamiltonian into device with limited connectivity, we tried to do a few simulations. So what I'm showing you here, it's a simulation of a system with 4 neutrinos, and here we are looking directly at entanglement entropies. Okay, so on the left, I'm showing you the single qubit entanglement entropy for 1 neutrino. Okay, and on the right is the 2 qubit entanglement entropy. So these are quantifying quantum correlations in the system that are generated by the evolution. So the system we are starting always in product states. So the entanglement entropies are always 0 for either partition. Okay, and then the interacting Hamiltonian generates entanglement between them. What I'm showing you here, the black curve, it's the ideal evolution of the entanglement entropy, both for the 1 and 2 qubit case. Okay. The orange dashed line is the maximum possible value of the entanglement entropy. It's 1 for one qubit and 2 for 2 qubits. Okay. And the black dots are the results obtained by doing tomography on the system. Okay, so extracting directly the entanglement entropy by evolving the system and measuring it. Okay, as you can see, the entanglement entropy you measure, it's substantially larger than the one that you expect to see. Okay, and this is caused by the fact that, like, pretending that our quantum device is a black box isolated from the environment is not really a good approximation. Okay, the environment, the qubits in the system are coupled to the environment, and this leads to the coherence, which when you look at it in terms of entropy, just increases the entropy. Okay, so in the limit where the environment was strongly coupled with our qubits, we could see every neutrino essentially decoherent, okay, fully mixed. So that's what you're seeing here essentially. Now, once you realize that, like, entanglement, so that the environment can affect the simulation, you can actually try and estimate and characterize the effect coming from the environment and try to undo it. Okay, so that's what's called error mitigation. And we try to do this in a couple of different ways. And unfortunately, I won't have the time to really explain you how we got this. If someone is interested, I'm happy to talk about it at the end. But essentially, we have two strategies to mitigate the effect of the noise coming from the environment. The A version, it's an error mitigation strategy, which is designed when the noise level is very small. Okay, while the B is designed when the noise level is very large. Okay, as you can see, the A mitigation doesn't necessarily do a good job, but the B one works reasonably well. Okay, with very large error bars and with substantial biases. Okay, but this is just to show that, like, it's possible to characterize the effect of the coherence and try to undo it in a sort of reasonable way. Okay, sort of reasonable because you see the errors you achieve here are not anywhere near what you might want to do. Okay. And this type of calculation is they're gonna get better only by having better devices somewhere. Okay, most of this is very difficult to remove in post-processing. Now, this is interesting in the sense that, like, understanding, as I was showing before, the entanglement evolution in these systems can tell you something about the flavor evolution. But at the end of the day, the actual observable that we care about is what we can measure on Earth about neutrinos, which is their flavor. Okay, or the information about their flavor and their energies. Okay, so the most important thing we might want to get out of a simulation of these systems is to be able to track exactly the one-body expectation values. Okay, so what I'm showing you here, it's the expected evolution for the flavors of these neutrinos, which in this case is the expectation value of the sigma z operator on every neutrino. And we have 4 neutrinos, 2 starting as nu at the beginning and 2 starting as a heavy flavor. Okay, and they evolve and oscillate around. Okay, so that's what we expect to see in the limit where there is no error whatsoever. The gray band that you might not see, okay, in the middle, okay, that's expectation that we have if the coherence coming from the quantum device is maximum. So if all neutrinos are totally decohered, every neutrino should lie here for every time. Okay, maximally mixed state. If you do the simulation and we just collect the data, okay, that's what you get. Okay, as you see, all the results are concentrated in the center, which is telling you that, like, the coherence is happening in the system. Okay, but you see very quickly that, like, if I didn't color code this data with the corresponding lines, you wouldn't have been able to tell what's going on here. Okay, the errors are just way too large to be able to predict anything essentially. Okay, so this is in a way kind of worse than what we saw for entanglement entropy. Now, this is the bare results, which are equivalent to, like, these black dots. Okay, I showed you before. Of course, we can try to do a mitigation. That's what we got by doing the mitigation. If you compare left and right, okay, you're gonna start to see that, like, some results that they start to get in better agreement with expectations. Like, for instance, like these orange ones, they start to get closer to the expected one. Okay, so overall we can improve a little bit the agreement. Okay, but not quite as satisfactorily as we want. And especially we have situations like these 3 points here, okay, which should lie up here, okay? So the even error mitigating prediction, it's on the opposite side of flavor with respect to exact one, okay? And if you look closely, you'll see that like the error in the mitigated version is actually larger than the one without the error, okay? That comes from like the mitigation strategy, but okay. But it's an indication that like the noise level on these devices, it's very strong, okay? So it's difficult to directly extract flavor information straight from this, okay? So these simulations here were done sort of in the fall of 2020, okay? And in recent years, there has been an incredible improvement in the quality of these devices, okay? So just to give you some figures, the device we used to run the simulations was an IBM device called Vigo, with a quantum volume of 16. So let me just briefly remind you what quantum volume is. Okay, that's one of the possible metrics to characterize the performance of a quantum device. And essentially, a quantum volume of 2 to the n, okay, tells you, roughly speaking, that you can run n layers of 2-qubit operations over n qubits with a fidelity which is better than about 66%. Okay, so quantum volume of 16, which is the one of the device we used, tells you that, like in this case here, n is equal to 4. Okay, so in principle, with this device, we wouldn't be able to run 4 qubits with 4 layers with a reasonable accuracy. Okay, so in our case, we do have 4 layers of 2-qubit interactions, but each one of those require 3 entangling gates. So the depth we have is actually 12, and that's why we got results as this. Okay, so we went to a depth which was bigger than the one this device could sustain at a good fidelity. Okay. Now, quantum volume of 16, in a way, luckily, it's been a number that has been improved very much. So what I'm showing you here, it's the evolution of the quantum volume as a function of time. Okay, for short ion devices by quantum. Okay, quantum volume of 16 is kind of like down here. Okay. Now there are devices with quantum volume equal to 32,768, which, if I remember correctly, it's 14 qubits. Okay, and very recently, like a month ago, Continuum also showed a quantum volume of 65,000. Okay, which is 1 qubit more. Okay, so we are more or less up here. Okay, at the moment, you see the growth has been very steady. Okay, so what we tried to do, we managed to get access to one of these devices, in particular the one used to benchmark to get this benchmark here, so a quantum volume of 2048, and we try to repeat the same type of simulation. Okay, so that's the results we got. Okay, that's 4 neutrinos. These are the same results as before, but instead of showing you the flavor content of a neutrino, I'm just showing you the probability of being of the opposite flavor. Okay, that's just an easier way of like representing all of them in the same time, because if you see here, the green curve and the orange curve are just one reflected to the other. Okay, so if you just look at like the probability of changing flavor, they are just going to show up together. Okay, that's just that, but it's the same results. Okay, the curves here are the dotted one. It's the ideal evolution without any error whatsoever. To perform this calculation, we only perform a single sort of throttle step, increasing the size of this time step. And this we know will lead to larger and larger error the larger is the time step. So that's why we are showing this solid black curve, which shows you the expected result, accounting from the fact that like we are doing a total error. Okay, so the results from the quantum simulation should lie on top of the solid black curve. Okay, and indeed they do. Okay, so these are for the two different neutrinos, nu0 and nu3, okay, and nu1 and nu2, which are supposed to be on top of each other. And as you can see, the results from the quantum simulation are perfectly in agreement with what we are, what you will expect. Okay. So this the reason for this it's mostly because of the quality of the operations that you can perform on this device, okay, and not necessarily because of the connectivity that you have, okay? Because we showed before, even in linear connectivity, number of operations you need to do, it's similar to this one, Okay, so this is just a proof that like the fidelity of the operations that you can do on this type of device, it's by far larger. Okay, so since I'm kind of running a little bit short on time, let me just skip this one real quick. So after seeing the simulation with 4 neutrinos that were very encouraging, of course we try to do larger systems. So these are the results for 8 neutrinos. Okay, the system of Hamiltonian is sort of similar. There is still some symmetry. So like neutrino 0, neutrino 7, they start with opposite flavor, but their evolution is the same. Okay, so we can plot them on top of each other. Okay, and this is a result obtained for the 4 different pairs of unequal neutrinos, if you want, in this 8 neutrino system. Again, this is a single step. Okay, the depth of this circuit it's a bit long, it's a bit larger. It's like twice the one as before. But still, the results are very, very good, in very good agreement with the expected ones. Okay, these were good enough that we started to think that like we can probably try to go beyond just doing single total steps at larger time steps and just do multiple steps. Okay, so increasing the depth much more. We try to do it with 4 neutrinos. Okay, and these are the results we obtained. So. Every point you see here, it's an additional step in trotter. Okay, so the circuit depth grows linearly as you move to the right. Okay, so it gets more and more and more and more noisy. Okay, the results are still reasonably good. So in this type of discretization, you see that the ideal evolution is essentially matching a trotter one. Okay, because the time step it shows here is small enough essentially for this to happen. And you see that like up to like time 20, okay, the agreement is very, very good. You start to have some disagreement around here, okay, and same thing for the other 2 neutrinos, okay, which is already at like 5 to 6 time steps, okay. Something to keep in mind here is that the results I'm showing you here are just the bare calculations that it's the bare measurements that we got out of the device. We didn't try to do any error mitigation here, okay, mostly because we didn't have enough samples to enough shots, okay, to try to mitigate errors, okay. But the disagreement you see here, likely it's possible to overcome it by doing more measurements, okay. And just to give you a scale, to do the calculations here at the end, okay. So this is a 4 neutrino calculation, but in order to save on measurements, we did 2 sets of simulations of 4 neutrinos. So we're using 8 neutrinos at the same time, okay. And the last points here require around 352 qubit gates, okay, which it's way larger than what we will have been able to do with the superconducting qubit devices we had before. Okay, so this is very promising, and it looks like in the not too distant future we might be able to do something that it's difficult to do classically with these neutrino systems. Okay, so let me skip this one. Okay, just to wrap it up, so in general, everything I showed you was simulations performed on digital devices, where you really try to apply the smallest number of gates that are required to do the simulation. And as I was showing you, there is a dramatic improvement on the quality of these devices, okay? But it's still, in a way, not so likely that we will be able to use hundreds of neutrinos for thousands of time steps in the next few years, okay? So, matching what you can do classically with this type of digital simulations is still going to be difficult. Okay, we could get close. Okay, but it will take some time before we start to like learn new physics we wouldn't otherwise by doing these digital simulations. Okay. In the meantime, there are 2 avenues to explore, I think, that can help us actually get past what you can do classically. And one is to use analog simulators like trapped ion devices. This can usually be done with like around 100 or so trapped ions. So system sizes which are much larger than the ones you can do on a digital device. And the nice thing about the Hamiltonian that describes neutrino evolution is that it can be mapped almost directly with the Hamiltonian that is simulated here. Okay, so there's a way of like designing a trapped ion system which as underlying Hamiltonian, the neutrino flavor evolution. Okay, so you will be able to simulate directly experiments probing that flavor evolution. And the other direction, which is also I think is going to be interesting, is to try to tackle these simulations in terms of networks and try to leverage the all-to-all connectivity in these systems. Okay, So since I'm getting near the end, let me just flash very quickly my summary. So I hope I showed you that like collecting neutrino oscillations are sort of an interesting, strongly coupled many-body system, which interestingly is driven by the weak interaction, which is something which is kind of peculiar. Okay, it only really happens in Kirchhoff supernova or in like in extreme systems. I showed that like even the basic two-flavor model, the resulting Hamiltonian can give rise to very complicated Hamiltonian simulation problems, which can be they're well suited but to be run on quantum devices, especially traptonian devices. The fidelity of these devices is increasing very much. I showed you results for 8 neutrinos, one-time step. Sort of more recently, there was a paper showing 12 neutrinos, still a single time step. So this is very promising. As a way forward, analog trapped ion devices might be a way of like studying this physics in larger systems and not the ones that you can simulate in a digital setting, possibly with restriction on the type of geometries you can describe, but that might be an interesting avenue. And also tensor network methods can be helpful in at least try to understand in what geometries or for what initial conditions we might have strong differences between the many body and the mean field picture. And lastly, as I briefly mentioned before, there is a big part of work which has to do in try to understand exactly in what limit the spin model I described today actually is able to describe the physics of neutrinos and supernova correctly. Okay, and that's all work that can be done more on the classical side. And with this, I want to thank all my collaborators for the works I showed you today, and all of you for your attention.
Thanks. So, any questions?
I have a question. So sure. You can hear me? Okay. So thanks for your talk. Sorry, I missed the first 10 minutes or something, so I might asking a stupid question. In which situations in nature, even in supernovas, is it an interesting question to combine several neutrinos, where they always say that they even don't interact with anything? Now we talk about 12 qubits, 12 neutrinos interacting. What is the effect of this of the correct stimulation of, let's say, 100 neutrinos to make a useful application of a quantum computer? Yeah.
Okay.
Sorry, you see my question?
yeah, totally right. So okay. In order for the interaction between neutrinos comes dominantly from like diagrams like this ones, which are like Z exchange diagrams. Okay. And the coupling constant here depends on the neutrino density. Okay. For it to be relevant, you need a large enough neutrino density. Okay. And essentially you have this two-body interaction with a coupling constant, which is one. Okay. So in core-collapse supernova, especially close to the neutrino sphere, okay, this term here, it's by far dominant with respect to vacuum oscillations. Okay. So close to the neutrino sphere, so say a few tens of kilometers from the neutron star, two-body interactions are actually the dominant flavor contribution to the evolution of Hamiltonian, at least like for flavor. Okay, these neutrinos also have momenta of like 10 MeVs, so that's the dominant energy, right? But for flavor evolution, the two-body interaction is actually the dominant piece. Okay, and as the question for how large of a system you need, that's delicate in the sense that like the information about the local density is contained in the coupling constant. Okay, so the idea is that you want to try to reach thermodynamic limit by increasing the box size. You're doing simulation in a fixed box, right? With the neutrinos, you try to simulate the same density with larger and larger boxes and try to extrapolate to the infinite thermodynamic limit, right? So that's more or less easy to do. In some situations, you can really do very large systems. In other simulations, it's more difficult. Okay, there might be arguments for why one expects to see effects. For instance, situation like this one. So here, I'm not sure if you were here already, but like here,
yeah, I was
right. situations like where you have thermalization, for instance, which come because you have a quantum chaotic system. Okay, you essentially only expect thermalization to work better in a larger system, not in a smaller one. The time scales are getting smaller and smaller and smaller. Okay, so some qualitative understanding of what is happening can be done also from small systems. Try to see if the behavior as increasing system size follows what you would expect, and then extrapolate, right? The direct qualitative information you will get using 100 spins versus 20, it's not necessarily clear. In the sense of like what you will get there, it's a possibility of having a more complicated geometry. Right. So the biggest constraint is really like with small n, you can't have that many energies and that many angles. Right. So the idea is to try to have a system which is large enough that you can have some richness in a distribution of angles of energy.
Okay. Yeah, thank you.
Of course.
Well, I have a question too.
Mm-hmm.
Thank you for your talk. It was very nice. And could you tell us more about the Hamiltonian that you used? How did you get it, and what are the issues that you mentioned?
Okay, so these two parts here, these are sort of standard, right? So this is just the vacuum part, and that's just a W boson exchange with the electron. So this is not controversial in any way. Okay, this term here, okay, can be you can get it directly by looking at the matrix element of these diagrams here. Okay, so that's also sort of robust. The part that it's not necessarily that it's not included in here is that so these are just forward scattering, so there is no momentum exchange. Okay, and the reason why initially people designed the Hamiltonians with just forward scattering was mostly because that will lead to coherent enhancement. Okay, in the mean field approximation, but at the same order. So if you just were doing just power counting, okay, at the same order as these diagrams, there will also be diagrams where there's a momentum exchange, okay, which are missing here. Okay, so the Hilbert space I'm writing here, every neutrino, the momentum of every neutrino are fixed, they are not dynamical. Every dynamical property here is just flavor. Okay, the full leading order Hamiltonian will also contain a piece which is momentum changing. Okay, which in order to describe, you will need to expand the Hilbert space of the system. Okay, so you're also going to need to add explicit momentum dependence, for instance. Okay, some of the effects we're seeing, like this thermalization, for instance, we don't necessarily expect that adding momentum dependence will really change the picture. Okay, but it's an open problem to try to quantitatively understand how those things are important. Okay, that's the main part which is controversial about this Hamiltonian. And the second one is really connected with the fact that, like, to do these simulations here, we are putting neutrinos in a finite box with boundary conditions, while neutrinos streaming out of a supernova possibly are better described as wave packets. Okay, in these basis where there is no momentum dependence, you can't tell any difference, right? But when you start to include also the momentum changing interactions, having wave packets or not will change the form factors effectively in this term. So there might be an effect also coming from that. Okay, both of those, in order to study them, you will need to substantially increase the Hilbert space. So the first thing that we have plans to do is to try to tackle them first on the classical side, using some symmetries, and then try to see if that's generalizable. Okay, so in general, you're always going to end up with like a two-body fermionic Hamiltonian, which we know we can deal with on the simulation, just maybe not with 100 qubits.
Thank you very much.
Sure.
So I have a related question.
Mm-hmm.
Yes. First, thank you for the talk. And considering this Hamiltonian, as you explained, all these terms more or less are very, I mean, classical in the sense that we know very well a standard model and how to calculate them. Therefore, I wanted to know what is the reason for these all these simplifications that you have explained. Is it just because we want to implement it in a quantum simulator, or there is another reason?
No. So this type of Hamiltonian was designed mostly to perform classical simulations before quantum computing was thought to be useful for doing this. Okay, and the reason behind it was that this should be the leading order contribution to the physics that happens for flavor evolution. Okay, even though you're missing this additional incoherent piece. Okay, the approximation of having it inside of a box. Okay. That's mostly in order to be able to describe the system, okay? And of course, one will need to understand better how impactful is this, okay? But until recently, there weren't enough controllable many-body calculation of these type of systems, okay? So it wasn't necessarily clear how big of a difference it would have made the meaningful approximation of these systems versus the full many-body. Okay, now we have a better understanding of the many-body physics of this, at least for small enough systems. Okay, and we are starting to reach the point where, like, we want to understand what the other pieces will do. Okay, I hope I answered.
Thank you.
Sure. Yes, I see Domenico has a question.
Yes. Thank you. Thanks again. Yes, I would ask you two questions regarding the BBGKY hierarchy you were mentioning before about the polarizations. So first of all, if you retain the second leading order with respect to the mean field approximation, do you think this may be a good test bed concerning ion traps if we want to keep track of entanglement between more than 2 qubits? And the second question would be, do you think that this kind of hierarchies in the master equation could be well faced by using setups like cold atomic clouds, where there is the same description in terms of BBGKY hierarchies?
Right. So that's a very good question. And so there has been some attempts to go to the next order in the BBGKY. What it looks like is that that's not necessarily very stable with different choices of closure on the order of the next order. Okay. The results are very sensitive, and they don't necessarily reproduce what you get by solving the full many-body system, which is equivalent to just solving the whole thing, right? And in some situations, one can actually, especially in the situations where you have thermalization, for instance, okay, one can actually show that the entanglement that you're producing cannot be described by any finite truncation of this. Okay. Now, in principle, it's not impossible to think of finding a good enough spatial closure at a given order that is able to mimic enough properties of at least low body observables. At the end of the day, we mostly only want like one body properties. Okay, that's where the most of the physics is, right? So it is possible to try to design a closure for the next order, which is parameterized in a way that can fit the many-body problem, right? And still reproduce most of the physics, right? And as you were saying, similar system like can also be found in like cold atoms, for instance. So that's a good test bench. One of the issues here, especially, is this all-to-all interaction, which is sort of difficult to find in cold atoms, right? And that's kind of like, so the entanglement that this piece can generate is sort of fundamentally different from short-range ones. It's actually weaker in a way. Okay, so I think like both of those experiments, both of those like lines will help you understand how to sort of fudge a good closure that will work most of the time, right? But the jury is kind of still out for there, right? And the nice thing about it, like once you have a good enough closure, you can start to do like Boltzmann transport. You can use it to derive a collision term to do that, right? So that's one you're actually starting to think about. That would be really nice.
Wow, thank you.
Mhm.
So thanks again for the interesting seminar and
Of course.
for answers to the questions.
Of course, it was a pleasure. Thank you for having me.
And so this concludes QuantHub seminar for this academic year. And I remind about the QuantHub conference on September 25, September 27 in Bari, Italy. And the regular online seminar will restart in October after the conference. And for details on the QuantHub conference, go and see the website that you see on this poster. Thanks, everyone.
Bye, everyone.
Thank you again. Bye.